same. So we're looking at how many d electrons they have. We're going to look at magnetism with them. So what you're going to do is you're going to take one of the little straws and put it on the polar paper. If this polar paper gets too, if the box gets too poked up, just move the polar paper, retape it. It'll be okay. And then don't do it so tight that it won't move, but let it hang down. Oops, too much now. Okay, so you want it to be lined up to the polar paper, right? So it's about the same length, so you can actually see. So when you take the magnet, you're going to actually see how much you can pull it before it releases and record the degrees. But you have to do it a whole bunch of times because it might let go sometimes too early. Okay, so it looks like we're getting a deflection angle. So see, we got like 20 degrees, now we're getting nothing, right? So that's why you want to try it a few times. Okay, so that was, we're seeing propulsion. So sometimes you have to flip it over. Okay, and so do it around 5 times, you'll get an angle of deflection. Okay, that angle of deflection, then you'll put into calculations. I'll put the masses and the amount of, so the mass of the substance that's in there, and you'll find a magnetic moment. From there, you'll identify which metal it is. Because right now they're just labeled A, B, C, and D, and E. And E fell on the floor. Okay, so you're just going to measure the angle of deflection. So if you get a chance before you go home tonight to measure these angles of deflection, I have both the neodymium dots, and then I'll also put in the neodymium flat piece. And depending on how much is in the straw, sometimes one works better than the other. But the dots seem to work pretty consistently when I was trying it. Okay. Make sure it's not dragging along the surface, or you will not actually see it move very much. Right? So you might have to tilt the box forward just a little bit. Seem easy enough? Yeah. Oh yeah, it'll be there this weekend, and the building is open.
Because sometimes the building's open, and then someone should be here.
Okay.
And open beforehand.
And then it'll be there Monday, so if you wanted to do the calculations, that's fine too. But I thought I'd show you what it was and what you were supposed to do. The second part is I said I would look at the exchange energies for this. We're all goofy. And I forgot one piece. Okay, so when we were looking at 3 electrons, what did we say the exchange energy was? 2. The only thing I forgot is that they don't have to be in order. So what we were talking about was we can have a blue, a green, and a red electron. And then we can have the green, red, blue, and the red, green, and the blue. So that was our, it could go into 2 other spots. Those are those 3. But it doesn't have to go green, red, blue in that order, right? So we can have blue, red, green. Okay? So the one that, when they were doing it in the book, they said, okay, this is 1, 2, 3. This is 3, 1, 2, and then this is 2, 3, 1. So electron 2, 3, 1. And then we can have 1, 3, 2. Following? So we don't count the first one that it started as. That would be 3 exchange energies.
It could also be 3, 2, 1.
Yeah.
What?
3, 2, 1. Or no? Because I'm just. Yeah, there's 2 more 3.
There's so many choices.
It it should be 3 factorial.
Yeah.
Okay.
So it's still missed. Go with what we did the other day,
I don't even know what we did the other time.
which is, okay, so what we did the other day was if you have these electrons that could go in the 2 other spots, that's 2. That's 2 more. If we have this one, that would be 1 more exchange energy. So there'd be 1 exchange energy up here, there'd be 2 exchange energies here, so we'd end up with 3 exchange energies in this picture. 4. That is also 3 exchange energies, as there are 2 for this one, 1 for that one, and this one can exchange with anyone because it's got the wrong spin. So if we use that, okay. Any questions that have come up about the homework yet? When I was saying you know how to do your homework, I was showing you how to use this.
So when we were talking about exchange energy,
Uh-huh.
when we had just like one spin on the top level, and then we still counted that.
We shouldn't. So if it's just 1 in either level, there's no exchange energy, it can't switch. Okay, so don't count a blank one. So this one would have no exchange energy. Now would this ever exist? No. Right. We would have 2 exchange energies and on the top. Any other ones we want to do?
Sorry, just remember that one has an exchange energy too.
It has an exchange energy of 2, because the bottom has 2, and the top one doesn't have any. Okay. Other things? So, if we talk about ligand field theory, LFT, then we're going to look at how the orbitals actually interact. We're really looking at MO diagrams, and so we're going to create an MO diagram here. And we're going to limit our MO diagrams that we make to the common coordination complexes, and at first we're going to limit it to sigma bonds, and then we'll expand it to pi bonds. But it's really describing, like we said at the beginning of this section, it's focused on the bonding. But it steals all the language of crystal field theory. So the splitting parameters, LFSE used to be CFSE, right? Ligand field splitting energy. What's crystal field splitting energy? They just slapped an L on the front instead. So all of the qualitative language got transferred from crystal field theory. The quantitative portions of the MO diagram are really what's the new crystal field theory. So if we look at, you've got your pictures from the other day? Yes? Your handout from the other day? Is that bring back? Symmetry on a so when we wrote MO diagrams, one of the rules for bonding was that they needed to be orbitals of the same symmetry and of similar energy those can bond, and if they can bond, they make an EN bond. So we can look at tables of how do we could actually go to the character tables and we could actually calculate our own symmetry labels for all of the orbitals. Or we can use tables, like that top table that says, what is the symmetry of an s orbital in an octahedral field? So the metal s orbital, so of course we're looking at just a sphere. If we look at that top row, it transforms as A1G. So it has a symmetry that's A1G. Do you know where you're getting that from?
Yes.
Now, from the last column of the table. And so then we also have PX, PY, PZ. Okay. How do those transform? In an octahedral field,
T1U.
T1U. Do you remember what the T stands for? Triply degenerate, right? There are 3 equal energy levels. So the p orbitals are equal in energy, and they have, so they're kind of 3 next to each other. Then, in an octahedral field, well, then we have our d orbitals. The dz squared and the dx squared minus y squared, we said that those were higher energy in crystal field theory. And so if we look at those two first, they get EG labels. What does E stand for? Doubly degenerate, right? So 2 equal there. What is the G? God, so they're even, and here it would be uneven through the point of symmetry. And then our other ones, dxy, dyz, dxc, those all transform as what off of the table? T2G. So it's triply degenerate. They happen to be Garad. And it's just the second one. That's where the 2 comes from. So don't worry about the 2 so much. So now we've got kind of the metal piece. If we're gonna draw the diagram over here, we put the metal orbitals on one side, and then we put the symmetry adapted linear combination of random, okay, of the ligands on the other side. And what we're going to end up with in the middle is our MO diagram. In this case, we're looking at an octahedral considering only the sigma bonds. So when we're filling up that metal side, we know all the symmetry labels now. We need to put them in with a energy factor here, right? Because on this axis is energy. So increasing energy. What's going to be the lowest energy state that we have for the transition metals? We take away electrons from the s orbital, right, when we're going to make ions. So that must be a higher energy orbital than our d's. And so we start with our d orbitals. We're going to make it a 4d because of which metal we're going to use. And then we would have our 5s, and up high, our 5p. And now we can add those labels back in. So 2 of these are EG. Then we have T2G. And up here, we have A1G. And then T1. Okay? If we look at the ligands, only thinking about sigma bonding, so imagining them kind of as s orbitals, we can have different combinations of how those s orbitals are kind of drawn for the ligands. So that's your south picture right here. So if all of them are the same phase, that is your A1G. If there's 2 nodes, that's the T1U. If there's only 1 node, that's EG. So if we were to write those in kind of order of energy, which one goes on the bottom? Is it better to have 0 nodes, better to have 2 nodes?
0 nodes.
0 nodes. So the A1G SALC, these are the pictures of the SALCs, goes at the bottom. Then which one goes next?
EG.
EG, and there are 2 possibilities, which is why it is an E. And then T1U. Now we're assuming that those orbitals are about the same energy, and we're just ranking them kind of in increasing energy on that south side. Pretty okay with that so far? Okay. So now we have to start combining things. So our A1G can combine with our A1G. What would that look like?
Do you meet in the center?
In terms of orbitals, what would it look like? It would be putting the s orbital smack dab in the middle of the one that has all the same s orbitals. Right? Putting the s orbital in the middle of that SALC. Okay, you're not seeing it. There's our metal orbital, and then there would be the ligands all around it, those s orbitals, and they would all be overlapping. They would all be the same phase. That would be the bonding interaction of the s on the metal and the s orbitals that are all the same phase on the ligands. Getting there? So what would be A1G antibonding?
All 4 in.
So let me put it in here about yay. So they'd be the wrong phase, right? The s orbital would be the wrong phase to overlap with the s orbitals on the outside. Yeah.
I'm just wondering about the T2G. Why there's some sort of sound to that.
Which what?
What happened to the T2G versus south?
Oh, I'm sorry. I labeled this T1U. Let me look. No, but it's T1U. There's not, the initial label on this is wrong. It shouldn't be T2G. It's T1U, which is why we're using T1U. So that's why it's not there. You okay with that one?
Well, why do we not have a south for T2G? I get it's not this one, but
There is not a sigma bonding combination that transform triply degenerate with a Grad label, so that's not even. Okay? So, if we look at T1U, if it goes through the point of inversion, you would have the wrong colored balls come out on the other side. Right? So that's why this is not T2G. And these are all of the combinations that we can draw for only having s orbitals on our ligands. Kind of like imagining them all as hydrides or something. Those are all the possibilities. So there's not a possibility where there's a T2G because that's a symmetry label. You don't have to have equal amounts.
So if we were to draw those for T1U on here,
For what?
for T1, if we were to blend the orbitals.
Okay, so we're going to do that in a minute.
Okay.
Okay. So now we have A1G and A1G star. And now we've got our next level is the EGs. How are they going to react? They're going to overlap. So a d orbital here, those two d orbitals, which are which ones? dz squared and dx squared minus y squared. Okay, so we draw it over here. How could those interact with one of the pictures that we have for EG? With the first one, right, it could have the overlapping ones here, and these are all colored in, right? So it's not interacting with the side orbitals, per se, or the side ligands. It's only interacting with the axial ones. So that is combining these EGs. And then EG star. And since they're similar energies combining, they're not going to be as stabilized or destabilized as we saw on the A1. There's not a repulsive factor in the antibonding as much. So, I don't know. We'll call this M. I don't know what to call it. Z? This goes with picture Z. So that would be one of the pictures that we could draw. The other picture that would be bonding that would go with that would be to use the XY oh, I did the bonding back, the coloring backwards. We want this to be bonding, right? So if we color that direction. See how that matches up with the d orbital that we want to use? It's the dxy, and this picture is one of our EG pictures. We're okay with that? So this is picture Y. So Y would go over here. If we reversed the phases, that would give us our EG star pictures. Now, T1U can interact with T1U, right?
Mm-hmm.
Right? Same symmetry. Okay. How are they going to interact? They're actually going to T1U, and this is too high, so I'm sorry. It just needs to be higher than this one we had before. T1.
So why do you place that one below and then above?
It is how much interaction the p orbitals actually have with the T1Us. So if we're looking at the p orbitals, so draw a p orbital, we'll draw this one, right? And it's interacting with one of our pictures here, right? So if we pick the third one, and I'm just changing the face because of how I drew it, it's very much right along the line of symmetry, so it's going to be either very stabilized or very destabilized because it's very overlapping. So this is picture W. That would describe one of those. So that's taking care of the EGs, the A1G, and the T1U on the metal. It's taken care of the T1U over here, the EG over here, and the A1G over there. Okay? So what do we have left?
T2G.
T2G. And so if it has nothing to interact with, it can't change energy. It moves straight over as it was. Let's start putting in some electrons. Okay. Let's put in, if we consider that we have 6 orbitals that are each giving 2 electrons on our ligand. So what we're really saying is there's 2 electrons on each of the ligands that's donating to the metal. So what would be an example of this? H minus. But would H minus have the p orbitals? No. So we won't do that. But chlorine, NH3, right? Because it has a lone pair that it could donate. All we're saying is there are 2 electrons that are interacting with the metal, which is all of our ligands. And so it's filling up all of these sigma bonds. Whether we mess with pi or not will change with the ligands. But for sigma bonding, they're all going to look the same in an octahedral field because they all give 2 electrons. So you're always filling up all of these. No? Yes? Explain that to the person next to you because it looks like there's a mix of, huh? And yes.
So it's an octahedral, and it's I guess everything's donating 2?
Yeah, because we have, it's octahedral, so that means there's 6 things attached to it, right? Mm-hmm. And so we're saying each of them is donating 2, so that means that we're going to have 12 electrons, each 6 orbitals, so we're not going to have a deal.
How is chlorine donating too?
I have not figured that one out. Because I understand NH3, but I didn't understand the hydride, and I didn't understand the chlorine.
Well, chloride would be donating 2 because it's a lone pair.
Okay.
2 electrons.
Reasoning. We have 6 ligands. Why? Because we're in an octahedral field. So we have to have 6 ligands if we're in an octahedral environment. And each of these ligands is giving 2. So that means if we have 6 ligands giving 2, then we have to have 12 electrons. So we need to fill 12 electrons over here. So that's what we do. Everybody good?
Yes.
Okay. Now on the metal, we can change the metal, right? And it's going to change the number of electrons. So now we have to know what metal we're dealing with to make this picture. And I wanted to use a 4D, so we'll pick ruthenium. And we're going to use ruthenium 2+. Okay. So how many electrons does ruthenium have? If we take away the S's, right, because it's a 2+, 1, 2, 3, 4, 5, 6. Woo! Okay, pretty good with that? So we're going to put 6 electrons in. We put 6 electrons in. Now, how many electrons do we have to fill that middle part with? 18. 6 and 12, 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, you caught up in drawing that?
Mm-hmm.
What is our HOMO?
T2G.
What is our LUMO?
EG star.
What was the prediction from crystal field theory about how the d orbitals were going to split? Three on the bottom, 2 on top, right? And these were the d x minus y squared dz squared xy yz xz. And if we had ruthenium 2+, which would have been a d6, we would have, we would have put in 6 electrons. 1, 2, 3, 4, 5, 6. This crystal field theory picture matches the important part of our whole molecular orbital diagram. Okay? That's why that's cool, because it's fast. This, not so cool, because it's not very fast. Okay? But does it make sense why we get there? What we really are doing is, this is a bonding orbital. If we are to fill the EG, it doesn't get indicated here, but that's actually an anti-bonding. That's the only part that's really missing in this picture, if we only include sigma, is that this is anti-bonding. Okay? Ready for pi?
What? Unless you mean pumpkin, no.
It's not.
No, it's not.
Maybe it'll someday become options.
Okay, so since we are really concerned with the HOMO and the LUMO, we're just going to take out that HOMO and LUMO portion of that molecular orbital diagram. Okay? So we have our T2G and our EG, which we, if we wanted to be specific, is an EG star. This is what it looks like in a sigma bonded only. And what geometry is this?
Octahedral.
Only works for the octahedral, so this is an octahedral specific one. We have 2 different possibilities, so I'm sorry if you drew that on the side of your paper. Scoot down to a new piece of paper and you need both sides.
Oh.
I apologize. Okay, if our metal is electron rich and our ligand is electron poor, but it has p orbitals. So this is when you just think about hydride, we don't have p orbitals there. What we can do is we can make this our new metal picture, and we can put the salps over here, just now we're gonna just do the souths of the p orbitals. How many p orbitals do you have on one atom? 3. How many have we taken care of over here?
I don't know anymore. 3.
Look back at the pictures. Are any of those p orbitals?
The
No,
T1.
those are on the souths, on the ligand. We have not used a p orbital. Okay. So, which p orbitals make sigma bonds? Because to be a sigma bond, it has to be on the internuclear axis, so only PZs, right? So now we have to take care of the PXs and PYs for our 6 ligands. So if we have 6 ligands and they have a PX and a PY, how many souths p orbitals should we have? 12. We could write 12 being all the same energy, but they don't fit going across there, so I'm kind of stacking them close together. And if we label these in terms of symmetry, they get grouped into sets of 3. Okay, but they have symmetry labels. So we have T2U, T2G, T1G, and TU. Don't worry about those, that would be on the table. You could look up the p orbitals. Are there any souths that are the right geometry to interact with any of them over here? The T2Gs. So we're worried about these 3 interacting with these 3. If this is electron poor, are there likely to be electrons in here?
No.
No. If this is an electron-rich complex, we'll at least have a few electrons in there. We'll keep with our same complex. It'll have 6 electrons in there. So what's going to happen? Well, we're going to get a bonding and an anti-bonding interaction, right? Because those haven't bonded yet, right? This was the orbital that didn't bond. The EGs get carried over. So this is actually the new molecular orbital diagram. We have the metal one, the souths, and the new molecular orbital diagram. Okay? Trying to draw them all in. Okay. So now we have to put our electrons in. Okay. Where is here? The delta was right here. That was the important one. Where is the delta here? Same spot. But we've lowered the energy here, and so now we've made that splitting energy greater. So if we have pi acceptor ligands, the splitting energy increases, right? That's what we just did. If the splitting energy increases, is it more likely to be high spin or low spin? Low spin. Where on the spectrochemical series would things that have a bigger octahedral field fall?
It's the end.
At the end. going to be acceptors. Okay? Pi acceptors. Now, on the other side, and okay, so now you know, you're going to have to leave room in the middle of what you're going to draw. Okay? We have the salts. Okay? So now we're going to go the other side of this. What if we have a metal? Actually, the metal doesn't change, so it doesn't really matter here. We just want that the ligand is electron rich. Okay, what's the question?
So the ligand list that we had, it said something about one side or the other being pi acceptors. Is it the side with carbon monoxide or the side with?
The side with the halides. 'Cause those,
Okay.
wait, no, the bigger octahedral field was at the beginning. The carbon monoxide and the
Okay.
carbon nitrogen. Because, right, they've got double bonds, so they could accept electrons and make we could draw right, that's how we're imagining them, where the sigma bond is going from the carbon to the metal, normally. But what we now see is that we could actually take the metal, donate back, and it would make something like that. Where the electrons are coming in. That's the picture of the bonding that's happening. So things like Cn minus, CO, things with double bond character are going to fall with this in. If our ligand is electron rich, right, these all have electronegative atoms pulling electron density away from them. If it's electron rich, maybe a chlorine, something like that. That's going to be the other end of the spectrochemical series. And having electrons actually means that we're going to change the energy of these salts that get put in. The occupied T2G ligands are a little lower energy. Because it's the combination of those. So if we have T2Gs that are full, so the ligand is full. Okay, now we go to combine these. Well, it's going to combine in the same way. T2G star and the EG. Now, we have to figure out how we're going to fill this. Let's just put I'll tell you what. So I'm sorry, erase one of the two of the electrons on the cells. Yeah.
I was just wondering if there's some sort of convention you're using for like capital E's and T's and non.
Yes. So if it's a bonding one, then it goes to lowercase. Or I mean, if it's something that's overlapping with another one. So it can be bonding or anti-bonding, but this has interacted with an orbital already. This one had not, so we keep it a capital. Okay, so now if we're paying attention to HOMO and LUMO, where's our delta? We actually changed where the HOMO and LUMO were. Okay, so our delta becomes very small. donor ligands. I wanted to use the same metal here, but ruthenium D6 won't usually bond with a pi donor, not 6 pi donors. Okay? Because if it would be filling that antibond more. So that's why I erased 2 of the electrons, because we did want to fill here. But if we fill more, then it actually doesn't bond and the complex is not stable. So only when the EG star is filled, but not the T2G star is filled, do we find stable complexes. So you could have 4 of the ligands having donation capabilities and the rest be sigma 1. Because you can have mixed ligands, right? We don't have to have 6 of the same thing. Okay, everybody's going. Okay, figure out what your questions are. You have 1 minute to figure out what your questions are. Talk to the person next to you. And then we're going to do another geometry.
Can I go home? We have 5 minutes.
It's really hard when you're trying to stay awake.
That's always my problem. Is how do I organize it in a way that I'll be able to get back to it?
Yeah, this doesn't make any bloody sense.
I know. So, just try to take notes directly in the form. This kind of stuff is really hard to do.
Yeah.
Sorry.
Nope, you're good.
It makes sense, which is really scary.
You're not thinking about it hard enough.
I know.
You're so exhausted, you're not even functioning well enough to know you're not understanding things. It's okay.
Yeah.
Okay, so questions you want to ask? Yeah.
The 12 South orbitals, the orbitals that you got over there on the left, I don't really understand these.
So to make pi bonds, we don't ever use PZs because PZs interact, let's say they interact with the s orbital, they would interact along the internuclear distance. So that would always create a sigma bond. So here we're only trying to take into account the effect of having pi bonding. So if we look at one of the p orbitals, so this would be like our XY d orbital, and there's a pi bond that is formed when it interacts with the px, the ligand. And so each ligand, and there's 6 of them, is bringing an X and a Y, so that's why we get 12. They get different symmetry labels because there's different ways. There's lots of linear combinations, right? It's group theory. Lots of different ways that we could organize those 12 orbitals, but they're the same energy in sets of 3. And same symmetries. So this is one example of what are we at? W? We do a W?
Yeah.
And that would be what N looks like. Oops, not in there. And here is that we've got interactions on that one, that one. So it's got pi bonding around 4 of the ligands. So 4 of the ligands are all pi bonding with that DXY orbital. Kind of crazy. Does that help? Ashton?
On the example with the ligand electron rich, where did those other 6 electrons come from?
Where did these electrons come from?
Well, I mean, there's 4 there, but then in the MO diagram there's 10, so.
Well, so 6 of them came from the metal, 4 of them came from the ligand to fill it up for 10.
So we're just assuming like same metal as the.
Yeah, so we wanted to use the same metal. So this is what it is if it's only sigma bonding. And then if it has pi bonding with a electron poor ligand, it looks like this. If it has pi bonding with an electron rich one, it looks like this. And that explains our spectrochemical series, because it's all ranked by how well it does p orbital donation, or donating into the pi.
So how is that determined across the, like the ligand values that you gave us? Where do they go from being pi acceptor ligands to pi donor ligands?
Well, it's a gradual thing where we'll have acceptors, and then right smack in the middle is, I don't know if we put H minus on there, did we?
No?
So H minus will be right in the middle because it can't do any pi bonding. And then we get to ones with p orbitals that have electrons in them. So there's not, I wouldn't draw lines. Because it depends on the metal too. Can the metal accept electron density? Right? Because if I did fill 6 electrons over here and had 6, then it wouldn't have made a stable complex.
I think once you said that the ligand is more important than the metal.
Yeah, so
Okay.
that's why it matters more what kind of ligand we have here. We have the same metal in both of them.
But if you change the metal, it would also change.
Yeah, no, it does change if we change the metal, but it's a lesser importance than changing the ligand. Any questions? Okay. So, where? But wait, I want you to think about something before we go. Okay? We can, when is it square planar complex preferred? This is that handout that you need to kind of go through and learn on coordination numbers from last Friday. You kind of have to know those. Okay? So D8s prefer that. So if we were to draw a square planar diagram here, maybe we'd start with platinum, because platinum would be a D8. What I want you to think about is, how do these salps change? We don't have the same number of salps anymore. Okay? So I want you to come back with a postulation on what you have over here, maybe using your handout so we can draw the things. So that's what we'll do on Monday. Our guest is not coming on Wednesday.